In this video, we're going to do the same example we just did, but with a new priority list, and we're going to compare and contrast our answers. So again, we have 5 tasks in order to launch our satellite into space, um, and we want to make sure we're following the priority list model in order to do it right. So let's say we're going to reverse the priority list. Instead of using A, B, C, D, E, we're going to use E, D, C, B, A, see what happens, and see if this gives us a different answer. And again, we're going to follow the same process. So I'm going to start by circling my ready tasks. Well, what's nice about this is it's the same project, so we have the same set of ready tasks, A, B, C, D. And so I'm going to go ahead and circle them. And this is an important thing with the priority list. Remember that even though E and D are listed as the highest priority, I'm not allowed to do those, so I can't schedule them in that order. So what I always do is I schedule the first ready tasks, which on this list is task C. So that's what I'm going to do first, C, which is going to take 7 hours. And notice that already the schedule looks a bit different. And I'm going to try to use the same color. C was 7 and is in green. So 1, 2, 3, 4, 5, 6, 7. Hopefully I can count properly. All right. Next is task B, and so that one we'd say is ready. Task B, or sorry, is in progress, I mean. Task B is ready. Next up in priority, that's going to happen in processor 2, which will take 5 hours. And we did that one in blue. Then task 2 is in progress, or task B, and is done first. So at hour 5, task B is done, and then I'm going to schedule my next ready task, which is A, which is going to take 6 hours. So A, 6, and that I used which color? I used color red. Apologies if any of you guys are colorblind. The color is not important. Cool. There's A. And that would give us our processor 2 would be at the 11-hour mark as A is completed. But before we think about that, I like to work my way from left to right. So at hour 7, C is then completed. And again, we could think over here back to at hour 7, C is completed. Sorry, I crossed out A. I did not mean to do that because A is not done at time 7. But at hour 7, B and C are completed, but not A. And as we're moving, even though we're kind of out of order in our priority list, this is one of the annoying things about the priority list model. I kind of have to revert back to, well, E. At any point I want to consider, well, when does E become ready? At hour 5 I should have considered, well, were any of these ready, because those were higher priority than A. And that's excuse me. That's what some of you may be wondering is, why did I schedule A here even though E and D were higher priority? But we probably should have checked at that point. I just forgot. But notice at hour 5, neither E or D was ready yet because only B had been completed. D has to wait for A and B, and E has to wait for C. But notice at hour 7, now C is completed. Again, sorry, pretend A is not X'd out. I can't undo it that easily without erasing a bunch of stuff. But basically now E is ready at hour 7. And that is the highest priority task, so I'm going to do that as soon as I can. So at the moment that one becomes ready, that's when I want to schedule that. E is 5 hours. And I believe I did E in yellow. Yes, I'm going to try to be consistent. And then once E has been completed, actually, now A at hour 11 is done. Once A is done, then D becomes ready. So D was not even ready back then, but now it is. So at hour 11, I can now schedule D, which takes 2 hours. And I did D in purple. And that would put processor 2 at 13 hours and processor 1 at 12 hours. And at that point, I'm now done because all my tasks have been completed. End of project. So that's that. That's just another example of using the priority. And that would just imply that this last hour of time for processor 1 is idle time because we didn't have anything else to do. And this would be our finishing time. And notice this, like if we're comparing this solution to the one we got in the previous video, it's way better it's way more efficient of a solution because that one took us a total of 17 hours with 9 total hours of idle time. This one took us 13 hours with only 1 block of idle time. And in this case, we'd actually refer to this as an optimal solution, and the book sometimes uses opt shorthand to refer to what is a finishing time given a particular precedence digraph and what is the actual perfect solution. And notice that it is dependent on the priority list. And actually, it's not necessarily a unique solution. There could be a lot of different priority lists that produce an optimized answer. And another thing you might wonder is, how do I know if it's optimal or not? That's a hard question to answer because it's very dependent on the tasks and the times in the project. But in this case, we know it's optimal because notice that if we were to add up all the processing times of all the tasks, that ended up being 6 plus 12, 18, 20, 25. So just to do a little math here about and looking at why this is an optimal solution, total time is 25 hours. And since I had 2 processors, if we just take the total time and divide by 2, that would give us 12.5 hours. And this is like the best possible solution because obviously if we have a total amount of time that it's going to take to do everything and we divide it up between different people or processors, this is kind of like the best way of doing it. There is no possible way of doing 25 hours worth of work in less than half the time with 2 people. And also notice that since it's not a whole number, and since each of our tasks was a whole number and we had to divide them up, there's no possible way to actually get 12.5 in this example because they're all whole. So obviously 13 rounding it up is going to be the best possible way of doing it, and that's one of the reasons why this one's optimal. You might not like following that logic might not always work for these problems just because of sometimes tasks are so restricted that it's impossible to actually do them in that minimal amount of time. But basically my point here is that examining the amount of idle time can help you really determine, is this optimal? I'm never going to ask you if it's optimal or not on a test, by the way, but you'll often be asked, well, what's the finishing time? And of course, the main reason I got into all this is I wanted to help you see the difference between why the priority list matters. It makes a pretty big difference in the outcome of the model. And notice I really did the same exact thing in both these cases. I just followed them using the set of rules, which is called the priority list model. And anyways, the last question, in order to actually solve random problems is how would I come up with a good priority list? What does that take? And that's exactly what we're going to do next week. So there's a couple different methods of doing that. One's called the decreasing time algorithm. The other's called the critical path algorithm. They're different ways of determining a priority list. Otherwise, we follow the exact same process, no pun intended, for solving these problems. We're always going to be using the priority list model, the same set of rules where we're checking for ready tasks, scheduling the first available on the processors, and making sure to never violate the priority digraph. But anyways, that's it for this week. See you all. Hope you all are well.